Yes. Hi, everyone. I'm Declan from the University of Edinburgh, and I'm actually working on a topic very, very similar to Manuel. We've been working on this on and off together, but we're taking it from two different directions. So today I thought I'd talk about some of the work I've done previously, but also some really exciting work that's coming up in the next few months. So when I talk about crack healing and the origins of this project, we're talking about damage and healing cycles. So apologies if this is a little bit repetitive from the one before. But when we think of how we see this in the field, there are many examples across fault zones across the world, where after large magnitude earthquake events, we see these drops in seismic velocities, followed by very long and slow recoveries of velocities over time, in the timescales of about months to years. So while we can see this in the field, it's also important that we can replicate this in the lab. So earlier on in my PhD, I wanted to get a sense of what is the magnitude and the time scale that we see these damage and healing events occur. And so in a very, very basic experiment, I took some rock samples and induced some seismic shocks, which is a fancy way of saying I hit it really hard with a rubber mallet and recorded some waveforms over time with some transducers. And so by looking at these damage and healing cycles, particularly we want to look at the coda wave sections because these coda waves represent wave paths, ray paths that have sampled the medium many times over. And we think of damage and healing. Typically we see this in rocks that have a lot of inherent heterogeneities, so things like microcracks, pores, grains, different mineralogies. All of these things add up that when you change them, when you create small changes in these heterogeneities, you create small changes in stiffness, strength, and your elastic properties, which are reflected in velocities. So we did some coda wave interferometry. So we built upon a code at Edinburgh, and we found that the magnitude of these healing events, at least in this lab scale, was about a 0.35% recovery in velocity over the span of about an hour, and that's just after a simple whack with a mallet. So coda wave interferometry gives us a path averaging effect of all these changes of all these little heterogeneities within the rock. But it doesn't tell us exactly what's happening at a micro scale. So there's lots and lots of competing models that accurately simulate these effects. There's lots and lots of theory out there that tries to describe what is happening at the micro scale. But I'd like to get to know what is happening at a ground truth. So first, I thought I'd give a quick intro into the equipment that we're using. So the kit that we have in the lab is called Storm Mjolnir, which for any Norse mythology fans is Thor's hammer. And this is an X-ray transparent deformation rig. It houses very, very tiny samples. So they're just about 3.5 millimeters long and just 3.5 centimeters long and 1 centimeter wide. We've got confining pressure, pore pressure, ram pressure, an LVDT to measure strain rate, and most importantly, some transducers to actively measure velocity, but also passively listen for acoustic emissions related to our deformation. This is a quick overview of the lab setup. So we've got our deformation rig in the back, got 3 pumps, some valves to isolate pressure if we need to, and this is all controlled by water. So all these pipes just have deionized water in them, and basically our sample sits in here. It's in a tiny little jacket, which then we can surround with water to create some confining pressure, and we can inject into that sample as well to create some pore pressure as well. So very, very simple to set up, which will come in handy later on. So before we wanted to progress into some more detailed experiments, we thought we'd decide which of our in-house samples that we have is the softest or the most non-linear. So what is going to give us the most exaggerated sort of damage and healing effect that we could then possibly image. So we've got some limestone, some dolomites, and some sandstones, and these are all picked because of those heterogeneities that I talked about before. And I took these samples over to Canada and worked with Alison Malcolm, who was at the previous workshop, and she pioneered this experiment to characterize nonlinearity through what is known as pump and probe. So essentially we have a very high amplitude S wave that we send through the sample. So it's a high amplitude, low frequency S wave, which is meant to sort of perturb our sample. And at the same time we fire a very low amplitude but very high frequency P wave. And the idea is that those two waves intersect and interact in the middle of our sample here. And there is a delay time of that P wave probe as it gets to the other side caused by the interaction of that S wave. And so these are a quick overview of the results. So here's our pump signal. It's about 100 microseconds long, so it's a 4-cycle shear wave burst. And our probe signal, very, very tiny, just a couple of microseconds. And so essentially what we're doing is we're repeating this experiment about 100 times, where we delay the probe wave by 1 microsecond at a time, so that it intersects with the shear wave at different phases of at the complete envelope of the shear wave. It will intersect with it. And so these are the results. So we got some really high delay times in the Bentheimer and the Brea, up towards 80 microseconds. And importantly, in the limestones and the dolomites, we only saw really a linear effect, mainly because these are just very highly cemented and they're just quite homogeneous. You don't really get those damage and healing effects that you would see. But something I thought was really interesting is that you can kind of see the imprint of this pump signal in the delay times of the probe. So in these little bumps, these peaks and troughs actually correlate with the peaks and troughs of our pump signal where it intersects. So there seems to be some sort of softening and stiffening as we have a change in particle motion of our shear wave. So there's a bit more work on that, but I thought we'd progress into our imaging. So we've moved forward with our Barea samples. We've got some imaging equipment in Edinburgh where we can take CT scans of our tiny little samples. And this is just a cross-section of one of the Barea samples. By doing some 3D tomography, we can actually convert our X-ray images into some computer 3D models. And we just do this through some 3D imaging software called ImageJ. Some of you might have used it before. But we know that we're working with a Barea, so we can say, well, we know that it's going to be mainly quartz and feldspar, and maybe a little bit of iron oxide inclusions as well. And so just by doing some basic histogram color analysis, we can see that this gray area is our quartz rock matrix. These slightly lighter gray areas are our feldspars. The black bits and the dark blue will be our pores. And there's slightly, but almost not quite black bits, which we've colored green as microporosity. So this is pore space that's just less than 2 microns in diameter. And these bright white bits are our iron oxides. So with X-ray imaging, it's a little bit counterintuitive. The bright white bits are actually absorbing your X-ray energy really well. So the iron oxides absorb, whereas the black, your X-rays pass through. And so by adding all this up, we can determine from our little sample that it's got a porosity of approximately 23%. And by segmenting our grains, we can determine that there's a range of about 100 to 800 microns in diameter in our grain sizes. So I've been working with some data that's been previously collected at a synchrotron by a postdoc who was a postdoc at Edinburgh, Alexis, and she worked at the CatFail project in 2019, or the Catastrophic Failure project. And in these experiments, she took a wide variety of samples to a synchrotron and loaded them until failure while capturing images. In this particular gray Barea sample, she applied a constant strain rate at a hydrostatic pressure of 30 megapascals and took 3D tomographies every 50 to 100 seconds. So this is a slice of one of those 3D tomographies. We've got 15 frames, and right at the end, you might be able to see that the rock starts to completely fail. It's hard to see, but there's a few shear bands that occur sort of in this direction right at the end, but to be honest, it's quite hard to determine frame by frame what exactly is happening at the grain scale. So to get a better idea of what's happening, I've been working on this software called SPAM, which was originally developed by Edward Ando, who was at Grenoble. He's now moved off to another place, but he's still actively developing this, and I found it very, very useful for this field of work. So I thought I'd highlight 3 examples. Oh yeah, if you were wondering, it is literally named after the canned meat product, Spam, which I think originated in, it's from a Monty Python sketch that I think Edward very much loved, and this is all written in Python, so it was appropriate. But yeah, so the first example I thought I'd highlight was this micro-cracking that was done by Stavropolo. They basically were looking at this very highly impermeable clay, which was proposed to be used in radioactive waste disposal facilities. And they were able to track and 3D render micro-cracking that was occurring due to water absorption. They determined that this was lowering its effective stress, which allowed further cracks to develop, and maybe it's not a good idea that they should use this clay for radioactive waste disposal. So I thought that would be very useful for some imaging work. The next one was done by Edward, who developed the project, and he looked at small displacements measured at grain boundaries and how cracks develop, and determined that small displacements at these grain boundaries are actually the result of fracturing at just an individual grain scale, which I thought was really interesting. And the next one is maybe a little bit ambitious for the project, but there's an example done by Stamati, and they were able to take their 3D tomographies and convert these to finite element meshes, and then accurately predict and reproduce the material response of concrete samples that they had. So they were able to predict tensile failure. So I've been working on the second one, the small displacements, and this is some work I've done with SPAM. So this is all done with cluster computing. And this is the exact same GIF that we saw earlier of Alexis's data at the synchrotron, but with some exaggerated displacement fields. So we can see that even though Alexis took these and stopped imaging right at the end where the sample completely failed, we actually see in these examples that the sample starts to favor a shear plane quite early on, just in the 6th frame. And then starts to accelerate. So each frame that has been processed is processed in comparison to the one before. So there you can see a slight acceleration as it starts to pick up on that shear band. But also interestingly enough, after it completely fails, there is a relaxation and a rebounding that happens sort of up in this area. So as the arrows start to come back, and then they rebound back upwards. But even though this gives us a good idea of what is happening, in terms of particle motion, it doesn't give us a full idea of what is happening in this micro scale and how this would apply to damage and healing cycles. And so for this, I've started work on segmenting cracks that have started to develop in the lead up to that failure. So this is similar to that 3D model that was created earlier, but instead now we're tracing small micro cracks, which is a little bit finicky, but it's I think it could be useful. So it's easy to track and display like catastrophic failure, but what is happening at the microscale before we get to failure? By segmenting individual micro cracks, we can look at how these coalesce up into a larger failure band. But what happens if we let these cracks heal under pressure? So what happens if we hold, instead of letting the sample get to its failure point, what happens if we let it sit instead? And so maybe this calls for a different experiment. So earlier this week, we've had lots and lots of talks about proposal writing, and I was fortunate enough to have already written one last September. So me, Ian Butler, Andrew Curtis, Alexis, and Manuel have contributed to this proposal to work at the Diamond Light Synchrotron. And we got word in February that this was accepted, so we'll be heading down at the end of July. We've got 4 days of continuous beam time to conduct some experiments. We've got a variety planned. We're going to try to cast a wide net, but importantly, we're on a very, very high resolution beamline for X-ray imaging, and the resolution of these will be about 8 microns per pixel. So going back to those grain diameters I talked about earlier, we've got grain diameters ranging from 100 to 800 microns, which should be a good enough resolution to try to capture what is happening at a very small, high-resolution scale. Right, so and the overall project, I guess, is, how do we recreate those hammer blows that I did earlier in the project? I can't exactly go into the synchrotron and whack a sample without getting, highly irradiated. So it has to be done within the cell, and trying to recreate that has proved to be a bit of a challenge so far. But plans for what we would like to do is, essentially what I described before. So in Alexis, this is some results from Alexis's work, where she was actively or passively listening for acoustic emissions, and noticed that there was, a very high acceleration of these acoustic events that would occur in the lead up to failure. So we think by monitoring, as soon as these start to accelerate, we could maybe reduce differential stress and see what happens at the grain boundaries and at these micro cracks. Do we see healing? Do we see anything at all? But if we don't, at least it gives us a sense of the scale at which these events occur. And then all the while, we'll be measuring velocity as well. So in conclusion, we're trying to create that link between the observations of what we see in the macro scale through Coda wave interferometry and these early displacement fields, but also what's happening at the micro scale. And if we can link velocity transients to all these things, I think that'll prove to be a really cool model and provide some ground truth as to what is happening in these damage and healing cycles.